So this is week 4 tutorial on the content taught in the course Introduction to Machine Learning by Professor Sudeshna Sarkar. I'm Pintu Kumar. I'm a PhD scholar at IUR-IT Bombay. So I plan to cover these topics today. So I'll give you an overview of what is Bayes theorem, conditional independence, and how it is used. So there are a couple of questions based on this in your assignment. Next, I'll cover a naive Bayes today. And in the session following this, Manak is covering, I think, maximum likelihood estimator and maximum a posteriori estimator, map estimator, and these kind of things. So, like, if you are interested in those content also, you can later join him also. And if you have any doubt related to this, the content that I'm teaching or anything that you came across during those lectures, you can ask me anytime during this session. Okay, so you can type in the chat box or you can also unmute yourself and start speaking. That's a full. So I'll start. So first of all, I hope that most of you are aware what a probability is. Probability of any event gives you the, like, what is the possible chances of occurrence of that event. So like if you toss a coin, both head and tail are equally probable. So the probability is half. So probability is always between 0 to 1. And more it is closer to 1, more probable the event is. Okay. So there is a concept in probability called conditional probability. What is conditional probability? So conditional probability gives you, so this is a notation that we commonly use for conditional probability. What does this mean is, given the event B, that means like if you know that event B has already occurred, what's the probability of A occurring? Okay. So I'll give you an example. Let's say we are tossing a coin. Head and tail are the two possible outcomes. So what's the probability, let's say, of a head given that tail has already came? So when you know that tail has already occurred, then there is a no chance of head occurring. So this probability is simply 0. Similarly, let's say you roll a dice. Okay, so what is the probability of 2 when you know that the number that you have got is an even number? Let's say you two friends are playing and you roll a dice and you can't see what's the outcome. Your other friend inform you that it's a even number. Then what is the probability? That it is 2. So there are 3 possible even numbers, that is 2, 4, and 6 that can occur on a dice. So probability of 2 among these 3 is 1 by 3, right? So formally defining what a conditional probability is, it is given by probability of A intersection B divided by probability of B. So this is probability of A conditioned on B. This is what we say. Okay. Now, if you just look at this formula and shift this P of B on the other side, you get this expression. You multiply P of B on this side, you get this expression, right? From this, if you divide now both the side by probability of A, you see that on the right hand side, what you are getting is, this is probability of B given A based on this formula. So this A intersection B is a commutative operation. We all know that A intersection B is same as B intersection A. So you can rewrite this as probability of B intersection A divided by probability of A. So you get nothing but probability of B given. Now whatever you have obtained, this is nothing but the Bayes formula, and it's a very useful formula in probability. Like many theories are based on this formula. So when it is used, let's say like you have knowledge about one. Let's say you know like what is probability of A given B, and you want to find out what's probability of B given A. So then you can use these kind of calculations to obtain your result. Now before getting into some examples based on this, I would like to cover this like theorem of total probability. Some people call it theorem, some people call it property. That's some choice. So this black rectangular thing that I have drawn is your sample space. Let's say this is your complete sample space, and you partitioned your sample space in, let's say, 6 partitions. What I mean by partition is like all these sets that I'm partitioning in, these are disjoint sets, And when you take union of all these sets, you get the complete sample space. Okay. So union of all this P1, P2, P3 to P6 is your complete set, and all these are mutually disjoint, like they don't intersect with each other. So this is something called partition. Now let's say E is an event and you want to find probability of E. How do you find probability of E is you take probability of E intersection with every event, every partition. Okay, so you take probability of E intersection P1 plus probability of E intersection P2 and so on till probability of E intersection P6. Okay. So when you see this E right now is intersecting only with P3, P5, P4 and P2, so it would reduce to something like probability of E intersection P2, E intersection P3 plus probability of E intersection P4 plus probability of E intersection P5. Okay. So this is a necessary thing to know when you are using Bayes formula. Why is it important is when you try to find probability of P in the denominator, this becomes useful. Okay, we'll see when we get to an example. Here in an example from I think last year's course run. So similar question is there in this year's assignment also. So the question says a spam filtering system has a probability of 0.95 to classify a mail correctly and 0.1% of giving false positive. What do we mean by false positive is that actually the mail is not spam, but the prediction is that the mail is spam. So it is false positive. So I think you might recall from the first lecture that it is something which is actually not true, but it is being predicted as true. Now also we know that 0.5% of the mails are actually spam. So it is asking us to find out, like suppose that you get a new email and the algorithm is classifying it as spam or not spam. Then what is the probability that it will be classified as spam? So I'll probably set up the notations for you first. Okay, so let's say this A is event A, N is the event that it is actually not spam. Okay, let's change the notation. So I'll use that if A is equal to N, then this means it is actually not spam. This is its ground truth. Okay. So similarly, A is equal to spam means it is actually a spam. Now when we look at the predicted values, so P is equal to N means prediction is that the algorithm is predicting that it is spam. It is not spam. Now P is equal to S means prediction is spam. Okay. So let's see what probabilities we are given with in this example. Let's see what all are we given with. Okay. So let me use some other so that
What
it is
was
high.
that A you used for? I just missed out on that. A.
A means that the ground truth, or in reality, what's the label. So if you are getting some email, it might be actually spam or it is being predicted as spam or something. So A is equal to N means it is actually not spam. Okay, I hope that's clear. So it is given that like probability of it classifying correctly a mail that is spam is 0.95. What does this mean is probability that prediction is okay. So it says the spam filtering system has a probability of 0.95 to classify correctly a mail as spam. So it will predict it as spam given that it is actually spam is given out to be 0.95. This is given to us. Next is, as I said, that like probability that prediction is spam when it is actually not spam. This is given out to be 0.1 to us. Okay. And also we are given that probability of any mail being spam. Okay. So this is, I'll just rewrite this notation. So in reality, it being spam is, this is equal to 0.5 by 100. That is your 0.05. So first of all, writing whatever is given and like what is required is makes your life easy in these kind of examples. Okay. So what it is asking is, what is the probability that the mail will be classified as spam? So it is asking us what is probability that uh, prediction is spam. This is what it is asking. Okay, probability that prediction is spam. So we will use over here, like when we get these kind of questions, what we try to use is, we try to use something called this theorem of total probability that I mentioned. So like when you look at any set, okay, let's say this is our sample space. If you have this set called A, then obviously the other part is A complement. And if you take union of these two sets, you will get the complete sample space. When you take their intersection, it is empty. So A and A complement always forms your partition. Okay. So we will use the same thing. So using these values that we have, we can like write spam is equal to, this is your P is equal to spam, given that, what is given, that your A is also spam into probability of A is equal to. Now from where do we get this? You just recall the formula of this conditional probability. So I'll just write it down here. So this first part would be probability of S intersection, sorry, P intersection A. I'm just using this shorthand notation. So this is P is equal to S intersection A is equal to S divided by probability of A is equal to S. Okay. And if you multiply it by A equal to S, then these two terms cancel out just to give us probability of this intersection. So that's why I'm writing it as this. Now, because I have this quantity available with me, this quantity available with me, I can use this. Okay. So plus probability of P is equal to S given A is equal to not spam. So A is equal to not spam is complement of whatever I have written over here. It is complement of A is equal to spam. Okay. And it will be multiplied again with probability of, I'll just admit few people who have joined late. Yeah. So into probability of A is equal to not spam. Okay. So we have these quantities available with us. If you look at this thing, I have already written it over here, the first thing. And you have this A equal to S also available with you. You have second quantity also available with you over here. And for this is nothing but what it is. This is probability of A is equal to NS, not spam, is equal to 1 minus probability of. So what is the probability that I made is not spam? It is just 1 minus the probability is spam. Okay. So you have all these values given. I have also written the AND formula. I want you to probably use your calculator to solve this thing, because this would require some calculation, some decimals. So you can use a calculator. That's fine. So I want you people to just comment down the answer, whatever you're getting based on the formula that I have. So in the meanwhile, like if it is not clear to anyone, any step you can ask while others are calculating. So this Mahadev, this last equation, how I derived?
Sir, can you repeat this question, please?
Sure, I will do that. I'll just do this. Okay. we are asked to find the probability of
Sir,
yeah.
Pinto, sir,
Ah,
let us complete the answer and you can address our question like immediately. Let us complete this calculation. I am doing the calculation in parallel also. Okay, he got
okay.
that. Uh,
So whoever was speaking, like, is the question clear to you? At least.
we got the concept. Now let's move to the answer now.
Okay.
Don't we have any division value here?
No, because we just have to find a probability of S right now. Okay, so right now we don't have any division. Yeah, Akshay, it's fine.
1 minus probability of A is equal to S is how much that value?
So A is equal to S
Is
is
it
given to be 0.05, 0.005. Okay, you can just subtract it from 1. See, I'm not sure whether you would be allowed or not, but like a machine learning course, you always would be working with a programming language, so Python and those things. So it is not a great idea to practice calculation also. Even if you don't like bring a calculator, not allowed to bring a calculator in the final exam, the questions would be very simple. I'm not very sure whether you would get or not.
So,
we are getting to a point 1425.
So I think I made a like I missed a zero over here. If you will include, you'll get one more zero, I think. You just see.
So can you summarize once again, please, sir?
I'll
I
do
didn't.
this. I think people have attempted. I'll summarize. So, like whoever's have doubt, so I'll just repeat first the theorem of total probability. Okay. Let's say you have this sample space. Okay. If you divide, let's say this thing into three parts. Let's say this is part one, part two, and this is part three. Okay. Now, if you have an event E, let's say this is your event E, this green one. So you can see that you can write E as E intersection P1. Okay. You can do this. Union E intersection P2. Again, union E intersection P3. This is clear for everyone. You can do this, like whoever have doubt.
yeah, it clears.
Okay. Now, if you want to use probability on both the side, you see that these sets that you are getting. So E intersection P1 is this much. Okay, so this is this much. The second part that you are getting, that is your E intersection P2. These two things are disjoint. They don't overlap with each other. Like they are completely distinct. Okay. So this probability you can write as sum. So this unions you can write as sum when you convert to probability. So it is probability of E intersection P1 plus E intersection P2. So this is probability of this plus probability of E intersection P3. Okay. So you can write this way, right? So I'm using the same thing over here. Okay. What I'm doing is I'm writing probability of spam as probability of spam with intersection. Sorry, I'll just rewrite the notation. So now getting back to the question, let's just fix the notation. So what I'm saying is, so you have a mail. Okay, you receive an email. There are two possibilities. It can be actually a spam, and it can be actually not spam. Okay. Now you are running you are passing this same mail to a machine learning model. It can give you two output. It can give you spam. So I'm using P is equal to spam, and it can give you P is equal to not spam. Okay. What you are asked is, if you are receiving any random email, let's say this is email 1, what is the probability that this will be classified as spam? That it is predicted value would be spam. This is what is asked from you. Okay. So I can write this as this. Let's say I received an email. So this email actually can be a spam, or actually it can be a not spam. Okay. So this email can belong to so if it is predicted as that it is predicted as spam, then there are two possibilities, that it was actually a spam, or this is an event, or there is a possibility that actually it was not spam. Sorry. Or there is a probability that it is predicted as spam, but actually it was not spam. Okay, there are these two possibilities. Now, when we take this probability again, as in case of theorem of total probability, this union is converted into sum. Okay, union is converted into sum. Now let's recall this definition of conditional probability. What I wrote is probability of A given B is probability of A intersection B divided by probability of A. Okay. If you take this denominator on the left hand side, what you get is probability of A given B is your probability of A intersection B, and this is multiplied by probability of A. So now wherever I have intersection, I'll replace this by this. Sorry, this is B. So whatever comes later, it is divided by that thing. Okay. So this is what we get. So wherever I'm getting this intersection, I'll replace this via this kind of formulation. Okay. So I'm writing this again in this form. So let's see the first one. So I'm doing this probability P is equal to S, given that actually it is spam. Now you remember we had to multiply with this probability of B. So this over here is probability of A is equal to S. Now plus the second term also I'm using the same way. So this is S, given actually it was not spam, again multiplying it by probability that actually it is not spam. Now is it clear how did we get this equation?
Awesome, sir.
Anybody has a doubt, like in any step, like how do we get this? Because on Bayes theorem you will get a lot of things.
Theorem is derivation is clear, but how to read it from the question, that's little bit still a challenge.
Okay. I'll try to make that thing clear also. So
Sir, answer we got as point not 1425, but it is not there in options.
yeah, so this probability over here, I missed a zero over here. So it is 0.005. Try this
Yeah,
thing, then
I
you will
take
get
that only.
with 0.005.
0.005.
Not
It is
0.05.
it is 0.95 multiplied by 0.005 plus
Yeah.
0.01 multiplied by 0.95 again.
It would be 0.995, right? Not 0.95.
How it is 0.995? Oh, yeah, correct. Yes.
Then
Yeah.
you might get.
Yeah.
Okay. So, like how to read the question? So, see, first line is written as a spam filtering system has a probability 0.95 of classifying correct mail as spam. Correctly a mail as spam. So, if it is classifying a mail correctly as spam, what does this mean is that actually it is spam and it is classifying or predicting it as spam. So, it is given that its probability is 0.95. I think this line is clear. Okay.
Got it, sir. Yeah, that's correct.
Next line is 0.1 probability of giving false positive. So false positive means like you have to recall from first class, false positive means that actually it is not spam, but it is getting predicted as spam. So this is what false positive means. Okay. So its probability is given as 0.1. And again, like this P of A is given to be 0.5 by 100. So you just have to.
Got it, sir.
Okay, so I'll move to the next question. This would use Bayes theorem now. Okay. So yeah, what it says is, so just remember that you got, because these things are getting used. So probability of prediction being spam, you got as 0.10. 425, right? Yeah. So just remember this. And you can read the question, this one. Find the probability that mail classified as spam by the system, the mail actually being spam. So what is given over here is given that mail has been classified as spam. So it says that given that it is classified as spam, what is the probability that it is actually spam? This is what is asked. If you look at what quantities we had available, it's just the opposite of it. So when you have opposites of it, you use the Bayes theorem over here. I request everyone to please mute if you're not asking. So yeah, so now how to convert it to like using Bayes theorem? Just we can, if you want to see, you can see this formulation. Okay, so here what would we do is, this is probability of P is equal to S given A is equal to S into probability of A is equal to S divided by probability of S. Okay.
Yes.
So this is what you have to do. You know this already, right? This is probability of P is equal to S. So, yeah. This you have already calculated. You just need to look at the numerator. I'll just write these values over here also. Okay. Not able to copy it. I'm sorry. Wait. Yeah. So I'll write it. These values that are required, I'll write it just over here. You can just try probability of P is equal to S given A is equal to S is here, I think it is 0.95, and probability of A is equal to S is nothing but yeah, 0.0. So you just need to put in these values to get the answer. Please try. Some of them have already tried. You can also try rest of it.
So 0.95.
No, answer is this one. I think first one is the answer. Yeah, 0.045. You can just take it. It would be 0.95 into 0.005 divided by 0.10425. You can use that. Now let's move to the next question so that we have some time left to cover naive Bayes also. I think the idea.
So division would be.
Please repeat.
Sir, I was asking division would be 0.10425, but
Yeah.
I think it should be P of A equal to S now.
It should be P is equal to P of P is equal to
A,
S. So
yes.
So this is what we have to find. So this should come in the denominator, the second part. Bayes theorem is actually very easy to see. If you see, like if it is A given B, this is probability of B given A into probability of B by probability of A by probability of B. What is happening is, in the numerator, we are trying to convert this to probability of B intersection A. This is what we are trying to do. So if we multiply this thing by probability of A, we will get probability of B intersection A using this formula for conditional probability. Then we are just dividing it by the second thing that we are getting. So easy way to remember is that this thing would come in denominator, and whatever is here would come as first element. Okay, and these things just get reversed. Okay, I'll move to the next one. So what it says is, this is similar to this, that given the mail is classified as not spam, so it is like given that P is equal to not spam, what is the probability that is actually not spam? This is what we have to find. Okay, so again using this theorem, not spam, given that actually it is not spam, divided by probability P is equal to not spam, and this should be multiplied with probability A is equal to not. So we don't knew this thing, right? So if you write over here, what we have to find is that predicted value is not spam, given that it is actually not spam. So if you look at this thing, that predicted value that is spam when it is actually not spam is 0.1. So just let me have some space. So if we look at this value that predicted is spam, given A is not spam, these two are complementary functions. Okay, so this would be 1 minus 0.1. That is your 0.9. Why is it complementary? So when you are given the fact that actually it is not spam, then there are only two possibilities, that it is spam or it is not spam. So these are the only two possible things. So the total probability should be 1. So it should be 1 minus 0.1, that is 0.9. So now you can put in these values. So this should be 0.9. This should be 0.995. And this also you can obtain as 1 minus 0.10425 that you calculated, right? Yeah, Divesh have already calculated. So this is 0.997. You can also try. Okay, so these are questions on Bayes theorem. I'm skipping one question which is almost similar. Okay, because otherwise we won't have much time left for naive Bayes, which is more important than this. Okay, so before going to naive Bayes, let's introduce two definitions. One is your independence. Okay, what do you mean by independence is that okay, if you want the answer, I think it is, yeah, this one should be the answer. B1 is the answer. When I solved it yesterday, I got this B as answer. Before posting, I'll confirm and write it over here which part is the answer. Okay. So let's move to something called independence. Independence is related to two events. Okay. So it is a relation between two events. We call two events as independent when they don't affect each other's they don't affect each other's occurrence. So I'll give you an example first. Let's say it is raining today, and other event is that like you had, let's say, idli in breakfast. So these two events are sort of very not related to each other. If it's raining today, it won't imply anything about whether you will have idli today or not. Okay. So these two events are sort of not influencing each other. Let's say you roll a dice, okay, and you also toss a coin at the same time. So if you get 2 on this dice, this does not tell you anything about what you would get on this coin. So these two events are independent of each other. Okay. So let's say another example I would give is you are surveying some people. So using a network, Jayashri, what kind of network? In network, the data that you get are sort of dependent. So if you have these nodes and edges, so this relation that you are getting, this sort of represents your dependencies. Okay, so the data that you have in a network are not independent. Okay, Bayesian networks. Okay, in Bayesian network, I'll explain. Okay, I'll explain in that term also. But before that, we need to at least look at what a independence is, what conditional independence is. That we can move to Bayesian network. Okay, sorry, I skipped that Bayesian network. I'll move to. Okay, so how it is defined is like if you are given that B has already happened. So in this case, let's say that you have rolled a die and you already obtained 2. Then it does not tell you anything about A, right? So this is what is called independent event. So it does not tell you anything about other events. So this actual, how it is defined is this thing, that probability of A given B is probability of A. But when you write it more clearly, so what this quantity is, A intersection B divided by probability of B. So I'm rewriting this first term using this formula. This is probability of A. If you take this thing to the right hand side, you will get this. Now you see in this definition, you have probability of B in denominator. This can be 0. Okay. So to avoid this 0 in the denominator, people have adapted this definition more, but this actually came from this definition. So this is the formal definition that we use for independence. That is, probability of A intersection B is given by probability of A into probability of B. Okay. This is definition of independence. Okay. This is not conditional independence. Now let's move to what is a conditional independence. Now, if you condition on some set C, let's say you have conditioned on a set C, then the whatever you get, this thing, this is also a probability distribution. Okay. So if you sum these values, you will get 1. It will be between 0 to 1. So it satisfies all your properties of a probability distribution. So this is also a probability. Now, if you talk about independence, given C, you get conditional independence. So this was definition for your independence. When you just condition everything on C, that C has already occurred, then you get conditional independence. Okay. So now coming to Bayesian network, like Bayesian network, I have not included in this, but I'll try to give some overview about it. Okay. So I'll give you an example. Examples are okay. Anybody has doubt? I think somebody.
In the previous case, you are saying that A and B are independent of each other, but they are conditionally dependent to certain other event, that is C.
No. So these two are distinct definitions. So this is for independence. So when you just talk about independence, this is how you define independence.
That's all.
Okay. And this is how you define conditional independence. So conditioned on C, this is the definition of independence. That these two events are conditionally independent.
Okay.
Okay. So conditioned on some event. So that event is C. Okay, before going to Bayesian network, let's look at this example. One thing is that this independence and conditional independence, though they sound similar, but they are not related to, like, related in the sense that they did not imply each other. Okay. So if you look at this example, so over here, A and B are two events. Okay. Let's see that these events are actually distinct events. So disjoint events, so they are not independent. So disjoint events are always dependent. This thing you need to understand, are always dependent. What do I mean by that? So if you are finding the probability of A, there is some, let's say, non-zero probability of A, let's say 0.2. This is some fictitious figure. We don't know what it is, but it is some non-zero quantity. Now, if you condition this probability on B, because these two are disjoint events, and you know that B has already occurred, then A can never occur. Then this probability is 0. So your probability of A given B is not equal to probability of A into probability of B. Oh, sorry, probability of A. If you want to use that intersection definition, then also their intersection is empty. So intersection's probability is 0, but they can have some non-zero probability, right? A can have some non-zero probability, let's say 0.2. This is also 0.2. So their product is not like 0.4. So yeah. Somebody requested to join, but he's gone. Okay. So here is an example that conditional independence need not imply independence. Okay. So A and B are two dependent event, but when you condition it on C, then they become independent events. So your probability of A intersection C is 0. and probability of B intersection C is something, and probability of A intersection B given C is again 0. So if you multiply these two things, you will get 0 on the left hand side, and you will also get 0 over here. So these two are conditionally independent, but not independent actually. Again, this is an example where independence need not imply conditional independence. Let's say A and B are your independent events, but if you choose C such that their intersection is empty, then again they become conditionally dependent after taking the condition. Okay. So now quickly getting back to Markov, this Bayesian networks. Okay. In Bayesian network, like I'll just give you an overview what is a Bayesian network. So okay, I'll come to Bayesian network in just a while. I have something over here. Okay, I'll just come to Bayesian network in a while. So before going to naive Bayes, there are two kind of machine learning algorithms. Okay, one is called discriminative, and one is called generative. In discriminative, what you try to do is, so this I'm talking about classification over here. I'm not talking about regression. So let's say you have two classes over here. One is green, one is orange. Okay. So what you try to do is you try to find a line that separate these two kind of examples. Okay. So when you are trying to find this kind of line, those kind of models are called discriminative models. Okay. This is a very vague but intuitive thing. This is called discriminative. Okay. In generative, what you try to do is you try to find the probability distribution of a class. So let's say for this orange string, you find like if you have some data point given with you, what would be its probability? Okay. You try to explicitly find probability for all the classes. So for this green dots also you will find. Okay. If you had some other class, you would have find for that class also. Let's say green crosses also you would have find. Now, when you have a new data point, what you will do is you will look at its probability associated with every of these things, and you will predict which is maximum. Okay, somebody had a doubt. Somebody raised his or her hand. Okay, I think that was the mistake. Okay, so this is what a generative model is. Okay, now when you look at any generative model, let's say you have a example like this. Okay, you want to predict probability of x given y, right? Now, let's say x1 can take two values, that is your 0 and 1, and your x2 can also take 0 and 1, and your y can take 0, 1, anything. Okay. Now, when you look at the quantities that you have to estimate from data, you will have to estimate this thing that when your x1 is 0 and x2 is 0, what is the probability that y is equal to 0? If your x1 is 0, x2 is 1, what is your probability that y is equal to 0? This way you have to predict three things related to y is equal to 0 for the four quantity, that is your x1 is equal to 1 and x2 is equal to 1. You can sum these three and subtract it from 1. Okay, that is one possible thing. And again, for the other one also, you have to estimate three quantities. Now, if you look at this example, this x1, x2 are very simple examples, that x1 and x2 are taking very simple values, that is 0 and 1. If you increase the possible set that it can take, let's say it can take 0 to 10, 0 to 9, and this can also take between 0 to 9, and you have, let's say, 10 features, then the number of quantities that we have to estimate is very high. Okay, it is very, very high. So you can't estimate all of this from limited data set. Okay. So to overcome this, we have something called a naive Bayes is one approach. In this, what we do is we say that, like, if you have probability of x1 is equal to something, x2 is equal to a2, okay, and given y, let's say this is xn is equal to an, what you do is you write it as probability of x1 is equal to a1, x2 is equal to a2, and sorry, I'll just rewrite this. probability of x1 is equal to a1 given y. So you split this first thing, okay? Yeah, given y, you multiply it with probability of x2 is equal to a2 again given y. So what you are doing is whatever you had in front, you are just splitting it. So what does this mean? You are assuming that this x1, x2, xn, whatever these features are, these are conditionally independent. Okay, this is what we are doing. So we are assuming that this is given given a label, these features are independent. But this is not a very good assumption. Like wherever these are used, these estimates of probability that we get are not very good, but they perform good on the classification task. Let's say this probability of x1 is equal to a given y, or x is equal to something given y, or y is equal to 1, and probability of x given y is equal to 0. These two values are not very close to actual values. But generally what happens is if the first quantity is bigger in reality, then using this method also we get this first quantity as bigger only. So this final label that we are getting, that thing is true. Like that is accurate, but these probability estimates are not very good. Now, just to say that some applications might require these probability estimates also. Okay. So for those kind of estimates, we move to something called Bayesian network that was mentioned. Okay. Here we don't assume that these things are conditionally independent, but using the domain knowledge, okay, we construct some network. Okay, we construct something called Bayesian network. And how do we construct it is, so you have some network, let's say A, okay, B, this is your C, okay, let's say this is D, then this is E, this is some F, and let's say this is some G. Now, what does this say is, I have not like included Bayesian network a lot, so I won't go into much detail, but I'll tell you what does this mean. So how do we construct this network? You have to use the domain knowledge. So if like the example that ma'am mentioned in going late to the office, you will see that the notes that she placed above were based on her wisdom. So there was not like formula which note to place above which. So it was based on the experience in that domain or the wisdom, your own wisdom. So that is what we call as domain knowledge. Okay. So you need human intervention over there. Your algorithm don't learn that thing on their own. Okay. Now what does this mean is, like, see, this C node is dependent on this. So these are arrowed thing. Okay. So what does mean? This is causing this thing. 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 So whatever way this arrow is pointed, you can see it that way. So A, B, and G all are causing this C thing. Okay. Let's say there is one more thing. That is your H. Okay. Something like this. So if you look at this thing, then all these things are causing this thing. This A, B, and G. H is not directly causing. But what Bayesian network does for you is, it says that if you condition on its immediate neighbor, okay, if you condition on its immediate neighbor, so if you condition C on its immediate neighbor, that is your A comma B, if you condition on these two events, that these two events have already occurred, then it becomes independent of everything that is not below it. I'll repeat this thing again. So it will become independent of H and G. Okay, so this will be probability of C given AB into probability of H given AB. So this is how you can split this thing using a Bayesian network. If you have constructed a Bayesian network, so given its immediate parents, okay, it becomes independent of anything that is not just below it. So it can't become independent of this, but it will become of this and J. So for, let's say, for example, for this D, okay, so if you condition it on C, then it has become independent of H, A, B, and G. These things should become independent of. So this is what a Bayesian network is. So this is sort of a advanced topic that won't be used a lot initially. And that's why ma'am also covered it in very not in very detail, but this is the basic idea behind Bayesian network. So using this, we are able to now simplify this x1 is equal to a. So if you had this a is equal to a1, b is equal to b2, you can break this more easily rather than finding all these possible combinations. Okay.
So, sir, just in the same diagram, just to clarify, if you can just go back to the diagram.
Yeah.
You are saying that the probability of event P, when you say that it is dependent on C, then it becomes independent of H, A, B, and the other events.
Yeah.
Right?
Yeah.
Because it is dependent on C, and how C is derived has it does not matter for P.
How C has it is D. Yeah.
Yeah.
Can you please repeat your question? I didn't got your question actually.
P, it depends on the immediate parent.
Yeah.
Not left, right, or above that, or any other attribute.
Like its independence, we can't say anything about whatever is below it, but we can say about the nodes that are above it. Okay. Yeah.
Okay. Okay.
Okay. So this is what I mean. Like this independence is also conditional independence. That probability of D conditioned on C. So if you take any example, so intersection with A, you will get probability of D given C into probability of A given C. Sorry, you will get something like this. So this is what you will get. So if there was one more, let's say C, not C, G, let's say, then this would have also split it something like.
And we do all these things to reduce the kind of like multiple combinations into some simpler one, right?
So number of parameters that we have to estimate, we try to reduce that thing. This is why we build this kind of Bayesian. Okay. So this is what a naive Bayes is. I'll just finish an example. It will take 5 minutes so that you know how to approach naive Bayes. So in naive Bayes, what we assume that this will split automatically. So we assume that it is conditionally independent. Okay. So this is sort of common in your text classification and those kind of things. It is very common in. So these are some of the applications. So because your text, if you see, if you look at a document that you have to classify, document has many words, let's say 10,000 words. So over here, if you have 10,000 options, and also every place has lot of options for word. Okay. So this would be like a very huge number of parameters to estimate. So in those kind of scenarios, we use naive Bayes. Okay. So I'll just do the first part probably. Okay. So others, if you are interested, you can stay, or like if anybody wants to attend minus, that is also fine. So this is a training example that is given. Okay. So ABC is your feature x1, x2, x3, let's say, and K is your class that is to be predicted. This is your class, or Y that we generally use. Okay. Now you are using the naive Bayes, you are asked to predict what should be the label for this. Okay. So like this is maximum likelihood estimator. I'll skip this, but ma'am has taught in this tutorial, this lecture 2. If you haven't seen, please have a look. So what does it say is we will choose something that will give us the maximum. So it is intuitive. Probably I'll cover that also. It is sort of intuitive. So we have quantities like this. Probability of Y, I'll use K only. Okay, let's say you have these two quantities. Let's say probability of K is equal to 0, given the features that you have. Let's say ABC you are given, and you have probability of K is equal to 1, given ABC. So whatever probability you are getting as higher, so let's say this first one is greater than the second one, then you should predict 0 plus. This is sort of intuitive, right? So whichever probability you will get more, you will predict that class. But this thing is very difficult to estimate directly. You can't estimate this thing directly. Jayashree, I saw your question late. I'll sort of try to answer that. You are asking if E and F are as its parent series. These two are independent of each other given D. Given the this D thing, given their parent D, then E and F are independent. Otherwise, we can't actually say. Okay. So I'll come back over here. Yeah. So this thing is very difficult to estimate. For that, what we do is, let's say probability of K given X, we again use Bayes theorem. That is the probability of X given K into probability of K divided by probability of X. Now, if you look at this denominator, then this all the data points, you can assume that they are uniformly distributed, or these are like IID samples. So this thing we can sort of ignore for the time being. So if we choose the one with maximum product, the class with maximum product, we are done. So here also we'll try to find out this only, that probability of A, B, C given K is equal to 0 into probability of K is equal to 0. Okay. And we will try to find out probability of A, B, C given K is equal to 1 into probability of K is equal to 1. Like when we have a new example to classify. And whichever we get more, we will predict that class. Okay, let's now get back to this example. So if you look at K, there are 3 instances of 1. So probability of K is equal to 1 is your 1 by 2. Because there are 3 instances of 0 also. So probability of K is equal to 0 is 1 by 2. Okay. Now, you have to look at this particular set of examples. So what we want to find is probability of A is equal to 0, comma B is equal to 0, comma C is equal to 1, given K is equal to 1. Let's say first we want to find this. So using the naive Bayes assumption, we can split it. Okay, A is equal to 0, given K is equal to 1, into probability of B is equal to 0, given K is equal to 1, into probability of C is equal to 1, given K is equal to 1. Okay, so this is what we have. So let's see, when K is equal to 1, these are the 3 options. When K is equal to 1, just a second. Okay, so this is the first row where K is equal to 1. This is another row where K is equal to 1. And this one is a row where K is equal to 1. Now, if we look at probability of A equal to 0, there is only one occurrence. Okay, when our A was 1. So what does this say? That it is 1 by 3. Because there are 3 instances, we got 1 probability. Again, for B is equal to 0, we have 2 by 3. For C equal to 0, C equal to 1, we have 2 by 3. So let's put all these values over here. So this one we got as 1 by 3 into 2 by 3 into 2 by 3. And we also had to multiply this thing by probability of K is equal to 1. So which we obtained as half. So this is what we got over here. So what it is? So this is 4 by 27 into 2. Let's leave it over here only, right? Next thing that we have to estimate is probability of A is equal to 0, comma B is equal to 0, comma C is equal to 1, given K is equal to 0. Now for K equal to 0, when we observe these 3 are at K equal to 0, for A is equal to 1, A is equal to 0, we have probability 1 by 3. For B is equal to 0, we have probability 1 by 3. For C is equal to 0, we have probability 2 by 3. Okay. So here we get 1 by 3 into 1 by 3 into 2 by 3. And again, half for the K equal to 0 thing. probability of k is equal to 0. What do we get over here? 2 upon 27 into 2. So which one is higher, 1 or 0? Obviously, probability corresponding to 1 is higher. So the correct answer is 1. So we will predict 1. This is how it is done, right? So I think we are like shooting the time already. So yeah, one more thing I wanted to mention is this smoothing thing. So like here we calculated the probability just by counting these instances. Let's say all these A were 0 over here. I'm just giving you an example. So all these A were 0 over here. This was also 0, this was also 0. And in this case, let's say in 0's case, all these B's were 0. This is a possible case, right? So in our calculation, this term over here would have turned out to be 0. This term over here would have turned out to be 0. And the final probability for both these things would have been 0. Then how to decide? So this is an issue, like if any of the term gets 0, it suppresses the contribution of other terms also. So to overcome this, what we do is we add a small number to the count. So here the count was 1 by 3 we were doing, 1 by 3. Rather than this, what we can do is 1 plus some small number, this can be 0.01 or something like this. And suitably, we can do this 0.01 by the number of terms that were there. So we can do something like this to avoid the cases where we get 0 probability. At least we'll get some very small probability. So this is something called smoothing, which was covered in it. Anybody has any doubt in naive Bayes or any?
How will we do smoothing in this? Let's say this 4 by 27 into 2 comes some value.
Okay, so while calculating every of these quantities, so 1 by 3, 2 by 3, you can add a small number over here. So rather than 1, you can add 1.0.1 divided by.
Let's say the value of 1 by 3 will be coming as 0. So then how will we do?
So the smoothing that you have to do is while evaluating these quantities. So you won't do at the end, but during evaluating these quantities, you have to do. So in the first one, you can add this like 0.1, and to compensate that, you can just divide it by 0.3. So
instead of 1 by 3, we'll use 1 plus L upon RL.
L into some quantity so that you it's proportionate to the same thing. So this you will do in every quantity. So this will help you escape that situation.
No, so what I wanted to ask is, instead of 1 by 3, we'll use 1 plus L upon RL. That's the
that's what you have to do. So here in all these things, you have to do the same thing in this also while estimating the probability of k is equal to 1.
Okay, thank you.
Okay, I'll stop the recording. If anyone has any doubt, he can ask.